Glider 9-1 Soaring Weather. In the soaring world, pilots are confronted with critical decisions from the get-go. Taking flight hinges on assessing weather conditions, ensuring they align with safety standards for a smooth soaring experience. Gliders, being gravity-powered, are in a constant descent through the air. To counteract this, pilots actively seek rising air, providing the lift needed for extended flights. Now, let's talk about the atmosphere. It's a thin envelope of gases surrounding the Earth, essential for weather phenomena and protection from the sun's rays. Despite its importance, it's remarkably thin compared to the Earth's vast radius. The majority of atmospheric mass is concentrated in layers up to around 164,000 feet. Water vapor, a variable gas, plays a crucial role in weather production. Its presence varies depending on location, influencing conditions like clouds, precipitation, fog, and icing. Understanding fundamental properties like temperature, density, and pressure is key. Temperature reflects the average kinetic energy of gas molecules, while density and pressure indicate mass per volume and force exertion, respectively. Now, let's touch on the layers of the atmosphere. The troposphere, where weather happens, extends up to about 36,000 feet. Above it lies the stratosphere, characterized by a slow temperature increase with height. Glider exploration typically remains within the troposphere, but ventures into the lower stratosphere introduce challenges like pressurization and oxygen requirements. In conclusion, while gliders primarily operate within the troposphere, understanding the layers above provides a broader perspective. It's a fascinating journey into the intricacies of our atmosphere, essential for safe and informed soaring adventures. We're delving into the fascinating world of weather forecasting, specifically focusing on the different scales of atmospheric circulation. Now, the microscale deals with small, short-lived features, like individual thermals, spanning 0.10 to 1 nm and lasting seconds to minutes. Mesoscale events, covering 1 to 1000 nm, last longer, minutes to weeks, and include things like mountain waves, sea breeze fronts, and thunderstorms. Lastly, macroscale events, with dimensions exceeding 1000 nm, endure for weeks to months, incorporating long waves in global circulation and embedded jet streams. It's interesting to note that these scales interact, with smaller features nested within larger ones. However, predicting weather becomes trickier as we move to smaller scales. For soaring enthusiasts, predicting weather is particularly challenging because the features of interest often lie in the smaller mesoscale and microscale range. So, our soaring forecasts begin by examining macroscale patterns that create ideal soaring conditions. We then consider mesoscale features, such as cloudiness and temperature structures, to fine-tune our predictions. Understanding lift types and the environments where they form is key to mastering the art of forecasting soaring weather. So, let's dive into the intricacies of these scales and unlock the secrets of the skies for optimal soaring experiences. Now, we're delving into the fascinating world of thermal soaring, a crucial aspect for glider pilots seeking those uplifting air masses. Now, thermals, these rising pockets of buoyant air, are the lifeblood of soaring flight. We'll explore their structure, atmospheric stability, and how to decipher atmospheric soundings for optimal soaring conditions. First off, let's clear up the convection confusion. So, understanding the fine line between a warm, sunny day with thermals and a stable, liftless day is our ticket to the skies. Now, the structure of thermals is a bit of a debate in the meteorological world. We've got the bubble model, envisioning thermals as vortex rings with rising air in the middle and descending air on the sides. It explains why different gliders at different altitudes experience varying climbs within the same thermal. On the flip side, we've got the column or plume model. Picture a thermal column shaped by warm air flowing into the void left by the initial thermal, creating a more common scenario where gliders flying beneath another can tap into the same thermal, even with vertical displacement. But, they're not always perfect. Wind shear can make them turbulent or even break them apart. Understanding these nuances is key for glider pilots to optimize their use of thermals and navigate the skies effectively. Now, let's explore atmospheric stability, an essential aspect for glider pilots. Picture stability as the factor determining whether we ascend or descend in the sky. In a stable system, displaced elements return to their original position, while an unstable system sees them accelerating away. For us, this involves understanding the dry adiabatic lapse rate, DALR, roughly 3 degrees Celsius per 1,000 feet, a key marker for atmospheric stability. Shifts in stability result from surface warming or aloft cooling, influencing the conditions crucial for glider pilots. Inversions, where a layer warms with altitude, act as a cap on unstable layers, impacting thermal activity. Now, let's consider moisture. The saturated adiabatic lapse rate, SALR, comes into play when moist air rises. It cools at the dry adiabatic lapse rate until its dew point, then at the saturated adiabatic lapse rate, releasing latent heat. Moisture adds complexities, making it crucial for pilots to grasp these nuances. Understanding stability is like holding the key to optimal soaring conditions. We've just scratched the surface. In our next session, we'll unravel more mysteries of glider meteorology. Air masses play a crucial role in creating ideal conditions for thermal soaring. The perfect mix includes cool air aloft with dry conditions, allowing surface heating without forming cumulus clouds. High pressure is favorable, typically linked to an aloft inversion that prevents cumulus growth into rain showers. Cloud streets, organized cumulus bands, offer fantastic soaring opportunities. They form after cold fronts, driven by brisk surface winds. These streets align with the wind direction, providing excellent downwind cross-country flights. Thermals capped by inversions or stable layers create this phenomenon. Thermal waves, illustrated, occur above the inversion capping cumulus clouds. With winds perpendicular to the cloud streets and increasing at least 10 knots per 5,000 feet, these waves can produce lift of 100 to 500 feet per minute. Cumulus waves share similarities but don't require directional shear. Both types can exist without clouds present, adding complexity to soaring conditions. Understanding these atmospheric nuances is key for maximizing your soaring experience. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.